Hello everyone, welcome back. Today we will be discussing an overall overview of variational autoencoders. We will not go into the details or the mathematics behind it, but we will try to explore first what are actually variational autoencoders and why we need it on the top level view. We will not go into the mathematical details. This we will cover in our next lecture. So now just to recall, I am repeating the variational autoencoder image over here again, and you can see that we have this as an input feature vector which is denoted by x, and this input feature vector is fed into the probabilistic encoder which is given as q phi of z given x, and then the output of this probabilistic autoencoder is the sampled latent vector which is z, and this z is again fed into the probabilistic decoder defined by p of theta of x given z, and the output of this probabilistic decoder is the reconstructed image. So now I feel that once we have finished my earlier lectures on probability and expectation, you are comfortable with the terminologies that are written over here, that is the p theta of x given z and q phi of z given x. We will not go into the details of this image right now. We will do this in our next lecture, but I am trying to make you comfortable with the terminologies that are discussed over here. So as you can see, we have this loss function defined like this. So as you might have finished my earlier lectures on the mathematical preliminaries required to understand this course, then you must be comfortable with these terms that I have written over here. The first one is the expectation operator that is carried out onto the probability distribution q phi z of x. So this is the same terminology that I have discussed in my mathematical preliminaries, that is you can write an expectation of a x as e of p. So here this p represents this probability density function, that is q phi of z given x, and the expectation is carried out over to this probability p of theta x given z. So this is our any random variable y, and what is this? This is basically the KL divergence that we have discussed in our earlier lecture, and you can see that it's a KL divergence between the two PDFs that are q phi and p of theta. So right now you don't have to worry about these terms. We will understand each of these terms in detail in our next lecture, but my aim in today's lecture is to discuss the overall view of variational autoencoders, that is why we need variational autoencoders. So the very first thing that comes to anybody's mind while discussing the variational autoencoder is the goal of these variational autoencoders, that is what it is trying to achieve. So the goal of variational autoencoder is to find a distribution q phi z of x of some latent variable, that is z. So here our latent variable is z. So we are trying to find a distribution q phi z of x. What is q phi z of x? Q phi z of x is this. So we are trying to find this q phi of z of x. Let me clear this out in order to make things more clear. So what is our objective? Our objective is to find q phi z of x from which we can sample this latent vector z. So we will be sampling z from this q phi z of x, and once this is done, what it is saying now? So you can see that which we can sample from z of q phi z of x. So what does it mean? It means that we are sampling z from q phi z of x to generate new samples x hat from p theta x of z. That means once we obtain the samples z over here, then we will feed these samples into this probabilistic decoder p of theta x of given z, and then we will generate new samples x hat. So that is our target. So please mind that I have written new samples. So new samples means the samples which are not present in this inputs. So if you have inputs having multiple samples like this, then this new sample, that is x hat, will not be one of these samples, it will be different sample. So it will be something from this distribution, but this sample will be x hat sample. But in case of autoencoders, it used to be the red samples. So here we represent the typical flow of a autoencoder, and the idea behind this autoencoder is to obtain a low dimensional representation of the higher level input, that is the image. So image here is the higher level input, and what we are doing is we are converting this higher level image into a lower dimensional space, that is the z vector, containing few number of ones and zeros. So this is being done using the encoder scheme that is defined over here, which is in turn basically a neural network represented with q phi of z given x. So now once the lower dimensional representation of this higher level image is obtained, what we do is then we will feed this lower dimensional input into the decoder that is defined as p theta of x given z. And what the role of this p theta x given z will be, it will take this as the input and produce the original image back. So that is a typical flow of autoencoders. So the representation here, which we call as z, are also known as latent variables. So these latent variables are basically the lower dimensional representation of the higher level inputs, that is, for example, image here over here, which is a image of 2. So autoencoders are great, but wouldn't it be great if we could feed encodings to the decoder that were not generated from the images in the source data set? So what I'm saying is, so let us say we have a MNIST data set present over here, and these points corresponds to the images that are present in MNIST data set. So what I am saying is, autoencoders are comfortable in reconstructing these green dots that are here, but wouldn't it be great if we could feed the encodings to the decoder that were not generated from the images in the source data set? So by saying that, we mean, suppose there is one more image over here which is represented by this dot, orange dot, but this orange dot image, it's not from the MNIST data set that we have. Is it possible that if we feed this to the autoencoder through a p theta of z given x, it produces this as the encoding? So is it possible that if we feed this encoding which is not from this MNIST data set, is it possible that it will produce a new image over here which is not from the MNIST data set? If we could do that, then we could create a new reasonable image simply by sending these bunch of different vectors to the decoder and observe their outputs. So if that is possible, then we could have used a pink dot which is not from the MNIST data set. It will be passed through the encoder network p theta z given x, and then it will produce the encoding over here, and then we will feed this encoding into the decoder and it will generate some new image that is not in the MNIST data set. If that is possible, then it would be great. But the variational autoencoders have no idea that the vectors we are passing to the decoder are valid vectors or not. Chances are that if we give a random vector to this decoder, we will get a bunch of random pixels back. So this is because the decoder assumes that these encodings adhere to some unknown distribution and does not account for encoding outside of it. So this decoder does not take these z vectors outside the MNIST data set. If the vectors are given outside this MNIST data set, then it will create a bunch of random pixels which are not proper numbers. They are just bunch of random vectors. So that is basically the problem of autoencoders which VAE tries to solve. Essentially, VAE attempts to make sure that these encodings that comes from some known probability distribution can be decoded to the reasonable outputs if they are not the encodings of the actual image. So this is the problem that VAE tries to solve. Essentially, VAE attempts to make sure that these encodings which are present here comes from some known probability distribution that can be decoded to produce reasonable outputs, even if they are not encodings of the actual image which are being presented by these green dots. So that is what variational autoencoders help in achieving. I'm sorry, I have made a mistake that these blocks are not p theta of z of x, they are q phi of z of x. This is also q phi of z of x. That is, it is this section, not this section. So the approach that VAE takes is a simple extension of autoencoders, and what it does is, instead of forcing the encoder, that is q phi of z of x, to produce a single encoding, that is, earlier we had a single encoding of a particular image, let us say this, represented by some 0.2, 0.1, 0, 0.3. Instead of producing a single encoding, it forces the encoder to produce a probability distribution function over the encodings. So instead of having a single encodings, we have a probability distribution function for each of the encodings that we obtain over here. So instead of having single values, we will have probability distribution function for each of the encodings. So that is what this autoencoder will try to achieve. So the decoder here will then sample from this probability distribution function and try to construct the original image. So that is the overall view of variational autoencoders. So let's discuss these things in more detail. So now, before discussing the overall view of variational autoencoders in more detail, let's discuss the concept of latent variables. So the latent variables are Z variables. We call them as latent variables because they are hidden variables. So let's go back to our original image here. So let's clear this again. So this is our latent variable that is represented by Z, and it is sometimes also called as hidden variable because it's hidden. You cannot access this. What we have over here is X. So you obtain the values of Z from X, and then from Z you go back again to X hat. So these are the variables that are involved in this variational autoencoder. So what we have here. So what we are doing is the latent variables are basically hidden variables as we discussed. So we will model it through this formulation where Z is the hidden variable and X is the observed variable, and the line that connects between these two is defined by a probability, that is probability of X given Z. So this means if your line is towards this side, it means you are finding the probability of X when Z is given, but if it is on the other way around, then it will be probability of Z given X. So this is important. You have to note the direction where the node is pointing. If the direction is downward side, then it is probability of X given Z, and if it is on the other way around, then it is probability of Z given X. So these edges are, the direction of these edges are important. So you have to keep note of that. So let's move forward. So what are latent variables actually? So latent variables Z corresponding to a real feature of the object that have not been measured, or maybe the technology is not available to do that. So they are actually the features which you cannot measure by yourself. So for example, we have this original image represented in terms of X. So what our encoder P of theta Z given X is doing is, it is converting this image into a variables that are the latent variables such as smile, skin tone, gender, beard, glasses and hair color with the values of 0.6, 0.8, 0.9, 0.7, 0.003 and 0.9. So these are one of the several latent variables that might be possibly present in the hidden layer. I have kept only these just to make you understand that what kind of latent variables are present in the hidden layer. So by saying that smile is 0.6 means this node is basically looking at the smile feature of this face, and this node is basically looking at the skin tone, this node is looking at the gender. In this way, each of the nodes that are present in this hidden layer will represent something or the other which you cannot measure by yourself. So these are the latent attributes. So what decoder will do is, decoder will try to use these latent attributes and reconstruct back the original image. So that is the concept of latent variables actually. So in the above example, we trained autoencoders on the large data set with the encoding dimension of 6. An ideal encoder will learn the descriptive attributes of these features such as skin color, smile, etc. in order to describe the observation in some compressed form. So this we have already discussed here. So in the above example, we have discussed the input image in terms of the latent variables using single value to describe each attribute. So for instance, what single value you will assign for a photo of Mona Lisa? So then the problem comes. So in this, variational autoencoders will try to help us in solving it. So here we represent a comparison between autoencoders and variational autoencoders. So here we are discussing only the smile attribute. So you can see that for 3 different images, as they are smiling in different order, we get different magnitude of smile values for these 3 images. So autoencoder will try to put these values in your Z vector. So this may be 0.98 as she is smiling a lot. This one is in middle, so it's like 0.6. This guy is not smiling too much, so it can be something like 0.3 or 0.4. So what autoencoders will do is, they will produce a fixed value of these smile features. So it will be like, it will fix the smile feature value to 0.98, 0.6 and 0.3 to 0.4. But in contrast, what variational autoencoders will do is, instead of putting a fixed value, it will try to learn a probability distribution function for these kind of images, and similarly for Mona Lisa and similarly for this actor. So instead of having a fixed value, it will have a probability distribution function formed for this smile feature. So with this approach, we now represent each latent variable for a given input as a probability distribution. So as we have discussed over here. So during the decoding process, we randomly sample from these latent state distribution to generate a vector as input for our decoder model. So what we will do in the decoder model is that we will randomly sample from this distribution and we will feed this into this decoder model to generate the image itself. So these decoder models are sometimes called as generative models, whereas the encoders are sometimes called as recognition models. And here encoder is actually P of theta z given x, and this is Q of phi x given z. And these are actually the z latent variables. So by constructing our encoder model to output range of possible values, that is, this is the possible range of values for the smile feature. These are the possible range of values for the skin tone. This is for gender, this is for beard, and this is for glass. So it's generating range of values for these features, and they are not generating only single values like in the case of autoencoders, but they are generating range of values in case of variational autoencoders. So if you sample from this Gaussian distribution, so let us say if we sampled the green and the orange one from this Gaussian distribution, and these samples you can observe that they are very close to each other. And similarly, if we sample the skin tones, gender, beard and glass, then we will come up with two set of feature vectors for the z latent variable. The one feature vector corresponds to the green sample and the other feature vector corresponds to orange sample. So once we feed this into the decoder model, it will generate these two faces. So these two faces you can see are the same faces that we have encoded from the input side. Why it is happening like that? It is happening because these two samples are very close to each other. So if they are very close to each other, they will generate images which are similar to the images that we have fed from the input. But for example, if we sample from this side of probability distribution function, this and this, then this will produce another feature vector, which is a pink feature vector of different values of smile, skin, gender and beard. And once you feed these feature vectors into the decoder model, I am sure that it will not generate the similar face. It will generate something different or some different face which is not into the data set of this face image dataset. So that's why this decoder basically is called as a generative model that can generate different features which are not present in the original dataset. So I hope now you are comfortable with the basic concept of variational autoencoders, the concept of latent space, the concept of latent variables, the probability distribution function, expectation and KL divergence. So in next lecture we will dig into the details of the mathematics behind this variational autoencoders, and I'll try to make it easy for you guys to understand the loss function for the variational autoencoder. Thanks for watching my lecture. See you next time.